If you needed to resubmit your solar house, your last opportunity for an appointment is today at seminar. Otherwise, turn in what you have now. We will resubmit for a new grade at the beginning of unit number 7. Tomorrow I may take the day off. I'm feeling a little bit better, but then by the middle of the day I bonk super hard. And honestly, if I just like stayed home and slept, it might be good for me and I don't need to be here for test days. So I don't know, I might be here, I might take the day off. I'm kind of keeping my options open. If there's a substitute, it'll be the homie that knows how to do everything, so you should be fine. Either way, tomorrow's a pep rally schedule, so you have a short period too to squeeze in a test. Number 1, absolutely you cannot afford to be late tomorrow. Like when you walk in, the timer will start at the bell. My substitute has done it during pep rallies before, and he knows the deal, and he's going to press go at the start of the period. Other thing that you should consider is, if the transitions take too long, he cannot let you go until he has all the papers. So if you're stressed about the time to get to period number 3, just write your own pass. You can tear off a little corner of part of the essay paper or whatever, and just write your own pass. And then either I or my substitute will sign that for you. But you've got to be here for the test. If that makes you late, we'll sign a pass for you. It shouldn't make you late. Because after this period, there's nutrition normally, right? Okay. Questions about anything I've said so far? Am I talking too fast? I just had so much coffee. I don't usually feel giddy from caffeine, but I kind of feel it. Okay, take out your study guides. Stars don't tell you what's on the exam. Stars just tell you where you need extra notes. Hey, little buddy. I got so many compliments for you on your article.
Wait, what?
People said that was such a well-written article about you, or that was such a flattering article to you. And I was like, oh, I haven't seen it yet. And then I finally saw it. Good job. Okay. Like some English teachers. People like it. How many of you use the star system at all? How many of you have found that the stuff with stars is like you're glad you checked for the stars, like it was beneficial to you? I have to warn every student in the room about something. This has been a really long unit. We started this stuff in December. So this is a lot like university, where you'll have like a couple of months and then a test, and then a couple of months and then a test. This is one where experience tells me that notes really matter. And I don't want to sneak up on you, so I'll just give you like a gigantic hint. There are significant number of points in the free response and the multiple choice on study goals that did not get notes in class. I always do that, but I just want to be really clear that you've built so many notes, it's easy to get overwhelmed, but don't forget the stuff that's out of the book where we didn't talk about in class. Okay. Stars. First and second law of thermodynamics. Electrical resistivity. Energy efficiency. Cogeneration. Depositional basin. The 4 grades of coal, which are anthracite, bituminous, and so on. Please look up, we added a word in this unit right around there called peat. Probably want to know that. renewable versus non-renewable, biofuel and digestion. Fission is not the same thing as fusion. Kids mess that up a lot. One of those is a word that we use in day-to-day conversation, the fusion of things. But for nuclear energy, we don't often talk about fusion. When we talk about nuclear energy, we usually mean fission. Hello, Brosie.
Hey.
Yeah.
Yeah. Mine's calling me like, the worst.
30 mixed egg layers.
Okay.
Mixed breeds. Where'd pig
They
go?
don't have,
Something.
but they're going to have more breeds like the week after. I was looking on the website.
Oh wow, good job.
Yeah. They only have,
Variety is important. But honestly, Rhode Island Red is kind of the best chickens anyway. So if you can talk to, I hope it's Catherine, or any human that knows,
yeah.
just like what would you recommend? We want to have a flock of about 30 chicks to end up with 20 strong egg layers.
Okay.
Yep. See, that's another thing that was on my mind. It totally scrambled. I'm sorry. Enrichment, moderation, chain reaction, meltdown. Study goals 1, 2, 4, 6. Nine, 10, 11. 13, and I don't know where to remind you about something, but in study goal number 12, you were supposed to define what a kilowatt hour is, and then early last week we did some math about kilowatt hours. Do you remember the calculations I'm talking about with like a microwave and how many hours and how much that costs you? That stuff is always on the AP test. There's always some kilowatt hour math. So I don't know, study number 12 is about kilowatt hours, but those notes are probably somewhere else. So those Monday the 28th notes, you probably want to put a star on that. Then there's a chunk of study goals where we have notes on everything. 18, 19, 20, 21, 22. That was a big chunk of notes, all the fossil fuels. 18, 19, 20, 21, 22. Study goal 25 gets a star because you needed things from the book and then we added in class. That's 25. 27 about coal. And children, I'd like to give you another little reminder. When we talk about dirty coal, what we're really worried about is the sulfur oxides, the quote-unquote SOx. Remember that like the dirtiness of coal is the sulfur. If you don't have that in your notes, you probably want to drop that now. You should have a ton of notes for 29 gets a star, 32 gets a star. 34 gets a star. 36, oh my God, today will be the third day on 36. 42 gets a star. 43, 45, 49, 51. And finally, I have a little heads-up warning for you. This unit is, I think, the first unit where there are a lot of pro-con topics. Like, should we frack for natural gas? Should we use nuclear energy? Is wind power better or not? Should we shift to renewables or not? Which energy is better for cars of the future? These are pro-con arguments. The College Board loves pro-con questions. They're not just asking you environmentalist stuff. So they're going to ask you, like, why would you choose coal? What are good things about nuclear energy? What are the benefits of fracking for natural gas? And a lot of my students, they just remember the environmentalism stuff, not the opposite side of the debate. Be careful. Energy stuff has a lot of things on both sides of the debate. And look for all that in your notes. Please switch to your nuclear energy notes. I'd like to finish that assignment today. I think that's 6.45? 6.5 nuclear? Nuclear 6.5? Yeah, 6.5. Okay, I know I'm supposed to focus and everything, but I want to show you guys something. Just before I start class, here's one of the reasons that I'm so scrambled. Look what I'm doing after school today. A homie of mine just finished 21 days fishing in Mexico, and we're going to butcher like 2 whole truckfuls of tuna and wahoo at my house later. So I'm a little bit scrambled, trying to get ready for that. Like right after school today, I'm going to go start butchering fish, and that's really intimidating because that's just the tip of the iceberg right there. Is that a hand? No.
Is he a professional?
What?
Is he a professional fisherman?
Nope. Nope. He just spent like his retirement money to go on a really extended long-range fishing mission. Okay. Yeah, some sushi at my house tonight. Let's make sure that everybody got the right notes the first time around. You can just check your notes, make sure you have this in there. Wiley, if you could please tear that earbud cord and then just throw it out the door, that'd be awesome. Okay. Wild uranium doesn't have a lot of 235, so you go through this process of enrichment, dump a lot of the 238, until you reach what's called fuel grade. You make that into little tiny pellets that look like tall aspirins. You stack them inside of these little straws called fuel rods. You bundle all of those fuel rods into what are called, if I don't remember, stacks. Put all of those in this big metal assortment called a core. And then you get the party started by throwing a single neutron emitter into that mix. It's actually a whole bunch of neutrons until one of the 235s becomes a 236 and goes pop. And splitting the atom is called fission. Make sure you know that term. All these terms you're responsible for. Splitting of the atom is called fission. Remember, that's a critical term. When the atom literally splits, the nucleus falls apart. You've made one atom into 2. On average, those 2 are extremely heavy molybdenum and extremely heavy tin. I think I warned you before, check your notes, you'll have to explain why that's so radioactive. Those are small nuclei with a whole bunch of bonus neutrons. Smaller atoms cannot hold all the neutrons that were stable as uranium. Uranium can carry all those neutrons no problem. That's very stable. It's not especially radioactive at all. But when you try to share those among these smaller decay products, there is no chance they can hold all of those extra neutrons. This does not divide cleanly. So you end up with highly radioactive waste products. The most radioactive thing on Earth is what we make. To some degree, this will still be decaying when the Earth gets sucked into the sun. The most radioactive thing that's on our planet is what we make here. You may remember I told you they're 7x or 12x heavy. Way too many neutrons. In all of that splitting of the atom, you also get some loose neutrons flying around, and you get a tremendous amount of heat. Those are the two things you have to worry about. The neutrons, because they can cause a chain reaction that would accelerate, like the spark in the firecrackers. Please touch your nose if I made that analogy in my class. Cool. So you have to, quote unquote, vocabulary term, control the neutrons, like smothering sparks in the room full of firecrackers. You have to find a way to collect all those neutrons so they don't cause a chain reaction. And of course, all this heat would build up unless you find a way to dump the heat, to transfer it away. That's called moderation. Trying to shed or dump the heat. You have to control the neutrons, moderate the heat. Both of these are to prevent this from turning into lava. And later today, we're going to ruin some nuclear power plants and look at what happened at 3 Mile Island, Chernobyl, and Fukushima Daiichi, where these turned into lava. I'm so bad at teaching this because A, we don't do this in my class very much. B, honestly, it's kind of been a big challenge for me to learn this much. I don't know what you don't know. I don't know how to help you. Please ask questions. In my other classes, this section of the lecture is driven by student questions. Can I help you with anything about that?
The neutrons divide differently every time the 236 breaks apart?
Yes. The question was, do the neutrons divide differently every time? And yes. There are some structural weaknesses in the neutron when you map, the nucleus of uranium. So when you map all those forces, the gravity and the plus charges and the negative charges, there's some average weaknesses. There's an area of the nucleus that's likely to give up, but that cookie can crumble a lot of different ways. There was another hand, yeah.
Is the water in the diagram how they cool it or how they moderate it?
Yes.
Okay.
Yes. Technically, I want to remind you that I'm teaching you 1970s nuclear reactors because the United States stopped building them then. Globally, there's some other fancy moderators, but we don't do those here. And essentially, it's some type of water for, I think, all but one of the nuclear reactor designs. This is funky water, expensive water in modern reactors. What else? Yeah?
Why is boron used in control rods?
Because the baby Jesus said that boron is a good neutron absorber. Technically, a lot of the shielding in the reactor is lead, because lead is actually a pretty good neutron absorber too. But for the rods themselves, I'm fairly confident in saying that boron is the best. Like, I've never heard of a control rod not being boron. But then again, I'm only studying 1970s reactors, so modern times, maybe things are different. Who else? These are helpful questions. So you're telling me that was just perfect instruction is what you're telling me?
Why are we using the kind of the, like, in the first movie we watched, like the German engineers made?
That's you mean how the Germans were all eating cookies during their simulated meltdown because the thing was so mellow that nobody had to sweat it? Yeah. Because we stopped, you know, we were an early adopter, and then we're like, guys, nuclear power sucks, and then we got over it. And then all these people were like, hey, but you can make it better, and we're like, oh, I just quit. So globally, we exited nuclear energy before cool stuff was invented. You know how like in Cuba, they only had like the old classic cars from before the revolution? 1 and 2.
Why don't we go back? Like it's just too late now, or what?
No, that's a good question. I mean, I personally don't support nuclear energy. I've got some nerves that aren't related to the reactor core. The flip side of this is we definitely don't want to be running the sketchiest nuclear reactors either. Like, there are relatively developing economies with much better nuclear reactors. So, like, Iran's not a developing economy, but, like, India has nuclear electricity, and it's, like, really cool. It's, like, modern and high-tech and rad. So, we definitely don't want to be running these. I think it's kind of a separate argument whether we want to adopt more nuclear energy. I would say no, but at the very least, if we were going to use nuclear energy, we should use modern stuff. 2, 3, and 4.
When you like control the neutrons, are you taking them away from the products, or are you just like taking the whole like radioactive product and like moving it away?
At some point, you do both of those. Control is specifically the absorption of neutrons. So control means you catch them when they're flying, so to speak. It's like putting a bulletproof vest in front of the shooter. Like you want to grab them before they get to another uranium-235. That's control. But you can imagine that the control rods would eventually fill up like a sponge full of water, and so you do have to also, the other thing you said, eventually those control rods have to come out and go into storage because they're all full up and they can't take any more neutrons. And remember that those will now be radioactive. Those neutrons will eventually fall off. Boron's a good absorber, but that's not forever.
Is it condenser leak for cooling down the whole system?
Yes.
Like, just consistently keep it cooling down.
Yes. Remember that if any time you shut off the blue, the red's going to go back.
Wait, what?
Yeah.
Oh.
I'll show you, because we're going to break reactors later, and that's how they all break. I'll show you later. It's a good question. The answer is yes, and I'll give you more on that later. Yeah?
Weren't the German reactors really expensive, and that's why they weren't that sustainable?
Yeah, absolutely. That's a good part of that answer. We can get electricity so cheap, coal, natural gas, that another problem with the modern nuclear reactors is that they're hell of expensive. You know, just building a reactor is way more expensive than anything else. And then, you know, when you build a nuclear reactor, you're making an economic commitment for eternity that you're going to maintain that nuclear waste. I mean, eternity in terms of our government lifetimes, you know, millions of years. So another reason that we don't do the modern German stuff is, like, yeah, we could, but I could build 5 natural gas power plants for that price. That's a good point. Thank you for saying that. Anybody else? It's so nice when you all speak. Okay, here we go. Once you get the party started, those things get hot. If it's getting too hot, you slow down the reaction by capturing neutrons. If you want more heat, you pull out the control rods, and that'll accelerate the reactions, which means you get more heat output. You can feather these control rods, see those arrows? To regulate how much heat is coming off the rods. And follow the red arrows, you in particular. That heat transfers to make steam. And then the heat transfers from the steam back out with the coolant water. Your diagram should probably say somewhere heat transfers. Because the nuclear reactor relies on the transfer of heat. Like, here's the one key confusion. Here's where the Simpsons got it wrong. The radioactive stuff doesn't go anywhere. Like, honestly, your exposure, like, if you live right next door to this nuclear power plant, you get way more radioactivity from like a chest x-ray or like a long flight. Like the radioactivity stays in there because this loop is closed and there's a lot of control in there and there's a lot of shielding in there. So watch my hand. Radioactivity is contained in this pressurized primary loop. You all have this label, right? Pressurized water reactor, the primary loop, that's what's radioactive, right? Because that water stays in there, it can't evaporate, it doesn't go anywhere. Inside the core, it's very radioactive. You will die fast. It sucks. But the whole point of the core is to keep the radioactive stuff in there. All those subatomic particles, they don't really escape very much at all. There's very high density materials there. But the heat does. You have to dump the heat. So you transfer the heat to make the steam that spins the turbine. And then just so that you can send back cold water, you have to take the heat away from the steam and dump it to the environment. So those are heat transfers. Like if I take cold liquid into a sauna, 20 minutes later, I will leave with some of the sauna's heat. Right? Because the sauna will be a little bit cooler because some of that heat warmed up my bottle. If you put like a hot pot roast inside your fridge, you just took some of the fridge's cold away and transferred the heat to the fridge, so you warm up the fridge for a while in the process of cooling down your whatever you put in there. I can't remember. So, red arrows always going right, blue always coming back. Happy nuclear reactor. Can I help anybody with the reactor part of this? Because once we're good there, we can start breaking them. Yeah, bro.
When the control rods go into the blue rods to then absorb the neutrons,
Yes.
where do those then absorb the neutrons go? Do they just stay in the boron forever, or do they transfer back into the fuel rods?
That is a good question. I'm trying to think of a way to... wetlands prevent flooding by temporarily absorbing water and trickling it out over the long term. Remember that? Control rods are like that. They take all of those extra neutrons, but now you have radioactive boron that's heavy isotopes of boron, right? The good news is boron's pretty good at holding them. So now that you have boron +1, boron +2, boron +3 neutrons, those will trickle out over an extended period of time. So you took a flood of neutrons and stashed it into control rods that will trickle them over time. You've made some mid-high level radioactive stuff out of some extremely high level radioactive stuff. Yeah? Yeah.
If somebody like broke in the core, would you not be able to fix it because it's too radioactive?
Ooh, well, it happens all the time. You can kind of take small exposures. I hate to give away the punchline early, but in your reading packet, the last table has these scaled radioactivity exposures, and you can see that there's like a maximum annual exposure for people who work at a power plant, at a nuclear plant. It's somewhere in the middle of this scale. I'll show you the scale later. And so, like, I had a job that I worked with radioactive phosphorus as a bioluminescent marker for DNA stuff because I was trying to figure out which guppies were humping which guppies. So I did DNA analysis on guppies working with radioactive isotopes. And you wear a little card. And when your badge turns yellow, you're done for the year. So you do as much research as you can, and then when like, oh crap, like I gotta take the rest of the year off. So you have like a maximum dosage that you can accept before you start really raising the odds of having a bad outcome. It's like you can play the lottery, but not too often, or you might actually win. And so there's people who do go work in there. And at some point, if everything is running right and you have fresh control rods that can be replaced by robots or whatever, you can even get into the core of a reactor. So like there are people who service the core, but that one hit, like that's their lifetime exposure. Like, Will, it's your day, bro. You gotta go work in the core, and then you're free for the rest of your career. Reactor core stuff. Nuclear reactor, nuclear energy, heat transfers. All those underlined words you gotta know. Are we done? Yes, okay, I'm getting a lot of nodding heads. Here's one thing I'd like to clarify. Your book called it the nuclear fuel cycle. Starts with enrichment, and then watch this. That stuff that used to be 235, it literally becomes other elements. Imagine if I told you that in this piece of brass, one brass atom, is brass even an element? Brass is an alloy, isn't it?
Yeah.
F. In this aluminum carabiner, one aluminum atom just became a lead atom. Like, you wouldn't know which one, right? Like, when you're looking at that, how can you tell which atom is which atom? So when you look at a fresh fuel rod compared to a spent one, they look the same. Nothing's, like, left. But individual atoms of that 3% 235 have now split to become other atoms. So you will definitely know it's spent because it'll be hot, like extremely hot. If you don't keep adding coolant, it'll turn to liquid. It's so hot. And you would know if you stood by it long enough because you would start to feel sick and then your eyeballs would melt and your skin would fall off and you would die. Because you've made extremely high level radioactive waste. That's the end product. We call that a spent fuel rod. Part 1, Part 2, Part 3 shown slightly differently. Cycle 1 is red, Cycle 2 is blue, Cycle 3 is really light blue. Yes? Here's what it actually looks like. There's this 3-mile island called 3 Mile Island. In the middle of Pennsylvania, or on the edge of Pennsylvania. 3 Mile Island has 1, 2 reactor cores. You can see the containment structures. It has 1, 2, Power plants, this photo is not very focused, but it has a whole array of wires that go all over the northeast area to distribute electricity. They take cold water from the river, and I don't know why they don't just put it back in the river, but they take that hot water and they spray it with a bazillion shower heads into these towers to dump the heat to the environment. A potentially slightly relevant example of how this works. I was taking a shower with my boy and we got in a fight because he says, "Dad, the water's too cold." And I'm like, "No, dude, this water is burning my neck." And he's like, "Yeah, Dad, but I'm all the way down here and the water cools off before it reaches me." Because when you drop that, all the friction against the air transfers all the heat to the air, right? You actually make a whole bunch of steam all over the shower. And the water that hits my poor boy when he was like 5 or 6 or whatever, when he was a little boy, like by the time it gets down to his height, it's already going to be way too cold. Same thing, you take all that hot water from the condenser loop and you just spray it into the air and a bunch of steam comes out like a steamy shower, and down underneath there's just like a cold mist of water droplets hitting the ground. It's very refreshing. When you take a tour, you can walk through there. They're just open to the environment underneath. Here's the famous one down by San Diego. There's a really good surf spot right there, where I used to surf for a couple of years of high school. 2 reactor cores. Huge electricity plant in the background. You can see all the wires to carry away the electricity to San Diego. Cold water comes in from the Pacific Ocean and leaves as hot water. That hot water goes out right here. So during hurricane swells, you get this weird southeasterly, like right up the coast thing. So if you're surfing a hurricane swell, you feel the hot water at your feet. It's kind of nice. Sometimes these break. Are we ready to break them? Questions? Breaking them? Okay, this is study goal number 40, what? 40. Study number 40. Children, I'm going to show you a slide with a bunch of words. Just read it. You don't have to copy all the words. I'll give you a couple of quick notes for this. Watch. At 3 Mile Island, this thing leaked. See that little droplet I made? There was a leak in the secondary system. You see that leak right there, that droplet, like a tear? Now watch my hand, because here's a way to test yourself. Watch this. And Hunter, this is what you were asking about. Watch this. If this leaks, what happens to this water level?
Lowers.
It goes leak, drip, 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 because the coolant isn't coming back, right? So it goes, and any remaining water gets turned into steam, and then there's no water left there. So what happens to the water going back to the core?
It stays hot.
It stays hot. So it's already at 700 degrees. It's just pressurized water that's trying to expand into steam, but those pipes and stuff are all really tight, like a pressure cooker. And if they get hotter, 800, 900, 1,000 degrees, that's just too much expansion energy. And the primary system blows. And now, this water starts to leak out. So inside the reactor core, it goes like a tea kettle, you know? All goes to steam. And inside the reactor core, water goes like this until there's nothing to take away the heat from the fuel rods. And they go 1,000, 1,100, 1,200, 1,300, 14, 17, 2,000, and around then they turn to lava. So this is 3 Mile Island, and this is a slightly fancier version of the drawing. This shows you how they regulate pressure, in case anybody's curious. I can show you the picture later. And this is the lava ball inside the reactor core. Now they eventually controlled this reaction. Somebody was like, whoa, 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 whoa. And they dropped the control rods. And they went back up, coolant, like opened the valve, whatever. Homer Simpson picked up the donut, looked up, and pressed the right buttons. So they got this under control before they had a full meltdown. You should know. 3 Mile Island was a coolant leak, partial meltdown. In case anybody's curious, 2 separate human errors. Somebody messed up and then somebody else didn't catch the mess up.
What would happen if it like fully melts down? Like what would they do about it?
Chernobyl.
So we just have like a wasteland.
A, I don't know what the plan was. B, I do know that this was a close call. So within like 1 to 3 minutes, if somebody hadn't dropped the rods and added coolant, the heat would have built to the point where the reactor core itself could melt. Everything has a melting point, right? And once all of this stuff melts, you give it another 1 or 2 minutes, and then concrete and steel will start to melt. And then everybody's swimming in the ocean. You know, like that stuff goes out. That would have been really bad. P.S. 1986, like 7 years later, that's exactly what happened in Chernobyl, Ukraine. I don't know which conspiracy you like better. Supposedly there's like a cancer cluster around 3 Mile Island, which suggests that there was actually some radioactivity leaking, which probably makes sense because no shielding is 100%. So if there's more radioactivity in the core, there's probably more radioactivity in the structure, probably more radioactivity outside. There's this weird conspiracy theory face-off about whether the cancer cluster is fake or whether the government lied and there was leakage, or whether the power plant lied and said that it was more under control than it was. I don't know. If you're ever interested, there's fascinating conspiracy theories there. Supposedly there was like a batch of Hershey's chocolate because Hershey, Pennsylvania has like it's right next door to 3 Mile Island, and there's actually cows there. And so like in 1976 or whatever this happened, somebody had like a batch of Hershey's chocolate that tested higher for radioactivity. Not dangerous, but there was appreciably higher Hershey's chocolate radioactivity, supposedly. Don't quote me on that. That's just something I read on the internet. You guys want to hear the worst thing about 3 Mile Island? There was a movie in theaters at this time about a nuclear reactor. It was a fiction movie where there's a nuclear meltdown because the United States public was nervous about nuclear energy. So they made a movie, like a fictional film, about a reactor meltdown, and it was showing in Pennsylvania during the time of the actual accident. So imagine how much it would F with your brain if you're watching a movie about a nuclear reactor melting down and halfway through the film the lights come on and the sirens say evacuate, evacuate, there's a nuclear meltdown. And I would think like, wow, that's a pretty big move from this theater. And then everybody runs outside and there's like sirens and fire trucks and police and like, get out of town, there's a nuclear meltdown over at the reactor. And I don't know, I always do that thing when I leave a movie and I start thinking like, what if this was real? And then to have like a nuclear reactor movie and then go outside and wonder if it's real and then everybody's saying, yes, it actually is happening, I think that would really mess with my brain. I think I would just run into traffic. I don't think I could take it. Okay. Anybody else on 3 Mile Island? A couple of facts you probably want to know about Chernobyl. It used to be Chernobyl is in Ukraine. A lot of students make the mistake to say it's Russia because the USSR was kind of figureheaded by Russia because the USSR was based in Moscow. So a lot of people think that Russia is the same thing as the USSR, but it's not. You know, like states in a country, sort of, or like nations in the European Union. So Ukraine is part of the USSR, or was part of the USSR. And you should definitely know that most of the radioactivity from Chernobyl went to a neighboring country called Belarus, which was among the poorest USSR nations. It's actually a big complication is that this did not happen in a wealthy part of the Soviet Republic. Now, here's a good way to test yourself. Here's a good way to test yourself. Watch this. Imagine that you combine the first and the second loops. That's Chernobyl. Really simple, really cheap. You don't need to do the pressurization stuff. You just bring cold water and the fuel rods make radioactive steam to spin your now radioactive turbine. Does that make sense to everybody? And with a single loop, it's just sketchy because if you lose coolant, it's all the same coolant. So a meltdown happens more quickly. There's less ways to intervene. Does that make sense to everybody? Chernobyl only had one heat exchange system. You probably have to know that Chernobyl was a simpler system. Like they combined primary and secondary or something. I don't know how you want to say that. But it's a simpler system. They combined cycles 1 and 2. And when you combine 1 and 2, please look up. A coolant leak means melting fuel rods. And I think Liam asked me what happens if you don't get the... Okay, well, here's what happens. Everything melted. Like the chain reaction went further, so the temperatures went higher. So the rods melted, and then the core melted, and then that heat melted the containment structure. And basically, this all became a huge ball of lava that went like 50 or 60 feet into the Earth's crust. And out of that gigantic gaping wound, about 100 Hiroshimas of radioactivity went up into the air. Now, one of the things that's really hard for my students is the difference between a nuclear meltdown and a bomb. Look, because there's so much 235, a bomb raises temperature really, really, really fast, like split seconds, right? Every neutron is hitting a firecracker in a bomb. This takes a while to heat up, so it's like a minute, and then a minute, then a couple minutes, and then a couple minutes. So over like 15, 20, 30 minutes, it just looked like a bigger and bigger fire until it went, and then all this dust went up in the air, and that's, you know, nuclear fallout, ashes that are radioactive. But it's a lot of radioactivity. Way more than a bomb. Way more than the bombs that America used in Japan. Way more. You should know, simpler reactor, you should know full meltdown. This is like the real deal, like the whole thing, like full exposure to the environment. And you probably should know 100x Hiroshima, I think. And anybody want to pronounce that for me? Is it Hiroshima or Hiroshima?
I think it's Hiroshima.
Like if you're into research, the stories about the firefighters at Chernobyl are like the most heart-wrenching thing. Because either they knew exactly what they were doing and just sacrificed their lives to save other people, and that's like amazingly heart-wrenching for me. Or they were lied to and went into a power plant that they didn't know was radioactive. But the stories about what happened to these firefighters, like some of them never came out of the building, some of them died on their way out, some of them died in the parking lot, some of them died that night, some of them died the next day. But like the firefighters in Chernobyl, like that is an amazing valor story in my opinion.
Did like a helicopter crew die too or something? Like they flew a helicopter over?
I know that they flew many helicopters. I know that they would try to drop water, and the rising heat current was so extreme that it would just evaporate or bounce off the water. And so they couldn't get the helicopter in the right spot, but they kept trying to like, you know, cut sideways into the rising air so they could drop water to cool that down. People were like, just get water, get water.
Yeah. I'm pretty sure like a helicopter crashed too.
That doesn't surprise me, but I don't know. You know, I was alive during this, and it just came to my attention recently. Like, I should have memories of this. I was 8 or 9 years old, and I have no recall of that time in my life. I mean, of this event at that time in my life. Drain damage. I don't know if you can tell here, but the water that touches the rods goes straight to the turbine. So all of this was inside the containment structure. So it was kind of a big, clumsy containment structure, and that means it wasn't very sturdy because it had huge reach. So like when the steel starts to weaken, it all collapses. It's important to point out that when you get this much radioactivity, your backup plan is for everyone to leave. So Moscow told everyone, get out, get out, get out. And you know the tricky thing is, all of those members of the Soviet Republic didn't really trust Moscow. Maybe, I don't know how much y'all understand this history, but there was a lot of like misinformation and manipulation within the USSR. And so the USSR says, leave, 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 leave. And everybody in Belarus is like, oh, you're always messing with us. This is just panic. And people are just suspicious of the government. And that turned out to be like a really tragic and unnecessary delay in saving people's lives. Then some of the people who were on the edges of that radioactivity, Moscow warned them, don't eat the food that captures radioactivity. Wild mushrooms, wild fish, wild berries. And the most tragic thing you're ever going to hear, rural Belarusians eat a very normal, poor person's rural diet of wild mushrooms, wild berries, and wild fish. Like, that's their native diet. And so when Moscow says, don't eat this stuff, they're like, oh, you're just trying to trample all over our culture like you've always done. And so the Belarusians wouldn't trust Moscow, and so they ended up eating all this highly radioactive food. So there's been like generations of impact from that. I screened a movie to show after school, and I couldn't sleep for like 2 weeks about like the types of deformities that are common in those bullseyes of radioactive exposure near Chernobyl, and it's so horrifying. Like the elevated rates of illness are just like totally, utterly nauseating. Like I'm haunted by the images that I saw in the documentary. Today there are the bullseye where nobody can go. They just keep covering it up with more containment structures. And those containment structures keep rotting, so they just keep adding them like Russian dolls. y'all know those nesting dolls that we call Russian dolls? So they just keep adding a bigger and bigger containment structure, but there's a limit to how big you can build things. So sometime between 40 and 60 years from now, we won't be able to build another containment structure over Chernobyl. And then we got no plan. Nobody knows. There's like bullseyes of you can go with government permission for a limited amount of time, then only national citizens are allowed, then it's recommended you don't go but you're allowed, then there's like a general health warning, but whatever, go for it. Funny detail, there's like spectacular deer in that exclusion zone because without hunters they get really big, you know? And so there's like a black market of like jump over the fence hunting trips in the exclusion zone around Chernobyl to shoot these gigantic, they're called red deer, and they have antlers that are like bigger than a moose. It's amazing. Okay. Anybody want to talk more about Chernobyl? Oh! Within 12 hours, you could measure elevated radioactivity falling on New York City. Within 36 hours, it could be measured every place we tried on the entire planet, including the field station at the South Pole. Global exposure within 36 minutes. 36 hours. Global exposure within 36 hours. Not extremely high exposure, but like everybody got an extra X-ray from Chernobyl. Yeah.
What happened to the neighboring country?
Well, Belarus was already poor, and the Soviet Union took a while to wrap it up after Chernobyl. So it's tough to weed out how many things already sucked and how many things got worse because the USSR kept Sovieting, and then how many things were bad just because of Chernobyl. But Belarus is a really unhappy nation. I mean, I don't know, the people are probably wonderful, but I need to say that like quality of life is really suffered, especially in those bullseyes near the reactor.
Did they evacuate too, or?
Yeah, so with differing degrees of diligence, right? So like the people in downtown Chernobyl, which is a city in Ukraine, like they all knew that there's a nuclear reactor. They were all heads up and they bailed right away. But some of the people that got more exposure due to the wind were like middle of nowhere farmers that hated the Soviet Union, and they did not evacuate. So some of the people with the highest exposure had a better chance to flee and just didn't because they didn't trust Moscow. Anybody else? How many of you remember the Fukushima Daiichi one that happened when you were like 10 years old? Some of you might remember there was like a tsunami in Japan. Fun fact, it made like a 1-foot tsunami in the Santa Barbara Harbor. That caused flooding, which broke electrical cables that ran the coolant pumps at a nuclear power plant.
That was the year I was in your class.
That was? Holy crap. Wow. Dude, you're old. You're 26 or 25?
Yeah, maybe 25.
So Toby was a little baby when you were in my class.
Yeah.
These pumps. What?
Oh no, it was just like, we talked about it and it was like relevant because it was happening.
It happened like a week before this lecture, I believe.
Yeah.
Yeah. Yeah, this was very relevant. I remember my website had like a news feed about stuff that was coming in at that time. Watch this. These pumps stopped running because they relied on electricity that was coming from a coal-burning power plant or a natural gas plant or whatever. So they had a full meltdown, and they also had a whole bunch of spent fuel rods that melted. Look at how many reactors there were. Remember I told you that Chernobyl sucked because it was such a big reactor? You can make them really snug if they're tiny. So one of the things about modern technology is they make a lot of little reactors. So they had 5 meltdowns of spent fuel storage and 1 partial meltdown of a reactor core. So the Fukushima disaster was actually 6 separate meltdowns because they had a lot of little reactors. That's probably worth noting. Everybody talked about how much radioactivity reaches us, but that's silly because that's a big old ocean. How many of you heard that there was like panic and people didn't want to eat seafood? You probably don't remember because you were 10. But there was like a lot of people talking about that. That was totally nonsense. It's a big old ocean. Like those neutrons spread out really far before they reach your seafood. All right. I've got like, I don't know, 18, 20 minutes to do like a few more study goals. Anybody have questions for me? Now it goes pretty fast. Sure, have any questions for me? Study goal 41. Study goal 41 says, what do you do with radioactive waste? There's 3 types of radioactive waste. This may already be in your notes. Low-level radioactive waste is a little radioactive. Like you can tell that there's stuff decaying, but that's not a huge threat as long as you keep it away from food and water. So low-level radioactive waste just goes into a good landfill. That's all. You just make sure it doesn't touch people's food and water. You just put it in the ground, landfill. That's like the gloves somebody wore when they were working on this, or like the badge that turned yellow because they got a lot of exposure. That's like a little bit radioactive, but not a big deal. Mid-level is like this plumbing right here. Like that's had high level in it. That's mid-level, like that's very radiated. That stuff needs to be buried in a really fancy case. So people call that encasement or entombment. It's like burying a corpse. Like you need a super burly casket with like fancy layers and a fancy hole in the ground with fancy deep covers. So mid-level is just complicated burial. But check this out. High-level radioactive waste, like the spent fuel, you can never ignore it. It needs to be stored, monitored, and maintained. That's important words. Stored, monitored, and maintained. Because it's going to keep decaying for pretty much thousands and thousands and thousands and millions of years. So like you can never ignore it, because the second you ignore it, it starts to melt down. 10,000 years from now, if there isn't some guy standing right there, that'll all melt down. 150,000 years from now, if there isn't somebody standing right there, that'll all melt down. There's nothing else to do about it. Yeah?
How bad would that be if all the waste we had just melted down?
The longer you wait, the less volatile it is, right? Like you wait for it to offload some subatomic particles so there's less hassle left when it does. But it would be really bad.
Like
Bad.
In like 10,000 years, if all the humans died, and like everything just like went off, like would every animal on the earth pretty much be affected pretty bad?
That's a bold claim for me to make, but it'd be pretty bad. It'd be a lot worse than Chernobyl, that's for damn sure. Yeah.
The control rods, what level of waste?
I don't know, dude, I don't know. I know that they're definitely not low. So it's either high level mid or low level high. So it's somewhere in that, and I don't know. I've heard so many conflicting answers that I've stopped searching for that answer. Yeah?
How do they monitor and maintain them?
So that guy needs to walk through with a Geiger counter and see if anything is offloading especially high. They have like a bazillion thermometers in there. And they're like, oh, barrel 48,000 is getting too hot. And so they have to like switch the coolant and put in more neutron absorption and better shielding or whatever. But it does need to be monitored like full time forever. So all the states in the union got together and they're like, hey guys, where should we put all this stuff so we can monitor it? And everybody's like, okay, wait, don't look. Let's do it in Nevada. Because everybody hates Nevada, right? And so the rest of the United States bullied Nevada. And Nevada's like, what? No, I didn't agree to this. And the whole US is like, yeah, you're Nevada. And so we did. We like started making this gigantic hole underneath a mountain. It's like the most expensive tunnel ever. And there's just like all these spiral tunnels that like corkscrew down with like all of these mine shafts drilled underneath this mountain. Because hopefully that was like the safest place we could think of to do all the long-term storage. And apparently there was like some nerd at all the meetings that was like, guys, excuse me, hey you guys. And everybody ignored this dude. So he went to a newspaper and like published his research like in the Reno Times or something. And he's like, guys, there's like groundwater and earthquake fault. And so we gave up. But I think we spent, I don't know, you could Google this number, $250 million, $350 million, whatever, digging that hole. And then like now we just have a really nice hole in the ground in the middle of Nevada. And all the nuclear waste is still inside all the reactors just piling up. People just don't take out the trash sometimes and you can't close the bin anymore. That's like every nuclear reactor in America. This is why I don't argue for nuclear power, because what are we going to do? It's forever. Almost like what happens in 10,000 years if the humans are gone? Like bad things, man. Really bad things. Yeah?
What if we shot it into space?
Oh, well, for one thing, it's a lot of rockets.
Yeah.
For another thing, like 1 in 10 rockets explode and like you get like a radioactive fallout cloud of death falling to the earth. If you take the entire history of all space programs, it would handle like 4% of America's current volume. Like the payload is too astronomical to consider. Space elevator, maybe? You've heard of a space elevator? It's like an orbiting satellite that's synchronous to the Earth, and so you have like a big cable and you can like elevator stuff up. So maybe someday, but it doesn't seem very viable. Like the sketchiness of that is pretty extreme. The best thing we can do is vocab, vitrify it, like turn it into a chunk of glass. Apparently glass is good for this. Glass.
Wait, can you define vitrify?
Yeah, make it into a chunk of glass.
Make the nuclear waste?
Yeah, so you take like a couple of barrels and you put them inside of a shipping container block of glass. Because I guess glass is a good shielder and it isolates heat and it's like a good neutron absorber if you put the right ingredients in the glass. And so the idea is, in terms of long-term storage, that's about the best idea we've got. Then when you've got all these chunks of glass, you take them on a container ship and you drop them into a deep sea trench. That's our best plan right now. That would cost like $40 bazillion, so in the meantime, we're just not thinking about it. Hey!
What would happen if you like made those into windows for houses? Would it be like super radioactive in windows?
I think that glass is actually a decent shield, but windows in houses are exceedingly thin, so it doesn't do you much good to have a thin shield. B, I think that this is a special glass. It's not plain silica. C, the stuff is still contained. Like there's a barrel, it's like a Jello mold, you know, it's like a slice of banana and a chunk of Jello. Like it's like a thing inside of the thing. It's not like blended and then glassified. And study goal number 42, there's this really hot debate. Some people are like, yeah, but no carbon. And that's kind of a compelling argument. There's like a lot of hippies that are worried about climate change that want to do nuclear. I understand that. I just feel like, yeah, but no waste disposal. I feel like that's kind of the debate today. Hey, no carbon, but like, hey, nuclear waste. I don't know, man. It's got fuel rods, but no carbon. The fuel rods. Heads up. Anybody speak Espanol? You speak Espanol? ¿Qué quiere decir secuestrar?
I don't know what that means. I've been for 2 years though.
Oh, that's good. Yeah. What? To kidnap. Please look up. Sequestration is to take all the CO2 before it leaves a power plant. That's in your reader. Get your reader assignment out. 6.6. 2. Take out 6.2. I think it's at the back of your packet. In the back of your packet. Sequestration is to kidnap the CO2. It means to take and store, to capture and hold all the CO2 in a power plant. You take it before it goes into the atmosphere. Sequestration is carbon storage. That's in that reading assignment, so I want to make sure you all know that word. It means to capture carbon. Part of the clean coal stuff, you know. And also please look up negative wattage. Negawatt is to use less energy. So negawatt technology is energy conserving technology. Like fancy light bulbs save electricity, negative wattage. So fancy light bulbs are negawatt technology. What is that? 3 minutes to go or 1 minute to go? 2 minutes? 4 minutes. We've got 4 minutes. Anybody want to ask me something from the reader? There's a lot of good articles in there. They do show up on the exam. I'm not kidding, they're on the exam. Anybody want to ask me about the articles? Ask me about articles? Hey, Womack, will you first smash the phone in your face and then stop streaming?
Yeah.
No, don't forget the phone smash.
Yeah.